So thanks for coming to this talk, and thank you for actually sitting through all of that. So you guys really, really, really want to know how to write a device driver. So that's actually what we're going to do today. I'm Kristen Accardi. I work at Intel's Open Source Technology Center, and I write device drivers. Thank you very much. And this is my lovely assistant, Val Hinson. Some of you may have seen her talk yesterday. She, in addition to doing file system development, also writes device drivers.
Wow.
So I'm
not when I can help it.
Well, no, that's not the right attitude. We're here to convince people that writing device drivers is really fun and really easy. In fact, it's so
way
easy.
easier than doing a projector.
Yeah, it's so easy that you could do it in less time than it takes you to figure out how to get X to send video out of projector. Anyway, so we're going to go through a little demonstration with a device that I've got made up just for this talk. Obviously, if we were going to do something in half an hour, it'd have to be a pretty simple piece of hardware, and that's what we have here. I don't know if any of you can see this, but it's basically a parallel port that has been wired up with 4 LEDs and a little switch. Oh yeah, we had a picture. It's right here. So this switch just grounds one of the input pins to one of the output pins. So you press it, you get an interrupt. And then these 4 LEDs are one line controls 1 LED. So it's pretty, actually, really simple interface, and that's what we're going to use to demonstrate. So, and to make things even more likely that stuff will go horribly wrong, we are going to show you that not only can you write a device driver in half an hour, but you could do it while you bake cookies. So I'm going to get started on that, and Val's going to get started on writing a device driver. So Val, what's the first thing
I don't know how to do this.
What's the first thing you do when you have to write a device driver?
What is the first thing that you do when you write a device driver? Anyone, any ideas?
Anyone?
Grab another device driver.
Yes.
Exactly, yay!
You win.
He
a
wins.
Cookie.
Yes, you always start by stealing somebody else's driver. Now, keep in mind, you have to understand the license of the driver that you're stealing. So luckily, in Linux land, we write kernel modules are all GPL, which means any other GPL driver is fair game to steal. So you can steal it and make your new derivative work based off of that original driver and save yourself a lot of hassle. So we've stolen the ACPI driver that I wrote last year. The reason we did that is because I already know what it looks like, and also it happens to be a type of device driver that is applicable to generic things like the parallel port, just generic platform devices. So the parallel port driver that we're writing is a type of driver called a platform device. So there's several different types of drivers in the kernel. When you start writing your device driver, you have to figure out what kind of driver am I? There's block devices, there's Ethernet devices, there are ACPI drivers, and there's this generic platform driver. There's all kinds of drivers, which I'm not even going to mention, but anyway, so you want to steal one that looks exactly like your device if possible, and the chances are there's a gazillion of them because, let's face it, there's only so many interesting pieces of hardware out there. So generally everything is exactly like something else, only with a different name brand on it.
We had to make up our own piece of hardware in order to write a driver.
I'm causing security issues here, I'm sure.
All right. I'm going to edit the series file while you're talking. So.
Okay. So I think what Val is going to be doing here is starting with a skeleton that I wrote. That I basically took the bay driver and deleted anything that I didn't care about. One second. All right. Baking cookies is hard. Anyway, so she's going to take the bay driver, which has been stripped down to its bare essentials, and she's going to show you how a normal device writer would start working. Let's see, read the directions on this. I don't speak Spanish. All right. You done with that yet?
Yeah. I pushed. We have the skeleton now. Driver's MISC.
Okay. Yes, driver's MISC. So this is a miscellaneous driver. It's going to live in driver's MISC. The The other thing that's always good to steal is the pile of headers. I've got a bunch of stuff in there I don't need, but I don't really care, and most of the time people don't care. It doesn't matter.
So you want to do the search and replace?
Yes,
Okay.
please search and replace.
Okay, so this is what you do. So we skip the part where we cut out all of the bits that are specific to the driver we're copying, because that would be really boring. And this is what we have left. Then
There's
what
cat hair on this.
I do have cats. Little cat hair never killed anyone. Okay, so the next thing you do is you go search and replace all of the name of the driver in the various function names. So in this particular case, the thing that you're using is it's bayonet. So we want to do parport blinky init, parport blinky exit, all that kind of stuff. So this is really complicated. Bay with parport blinky. Okay.
Well, I'm done with my part.
I want to do this one, right? Yep.
Right.
Yep.
Okay, so as she's going along, you can see some of the things that are of interest is for most device driver types, you're going to have to register yourself as a particular type of driver. For this one, this device is so simple that there's nothing really to say except what your name is, and normally you'd want to pass in some other information, but we don't need to here. A lot of drivers, like the block driver interface or the character driver interface, will have you register a set of entry points for your driver so that the operating system knows how to do things like probe for your devices, or it knows how to write to your device or read from your device. So with the platform driver that we're doing today, all we're doing is registering as a platform device, and then we're going to unregister if we fail and in the exit path. Okay, so after she's done getting this basic stuff in, the next thing that she's going to have to do is put in some basic init code.
Do you want to explain how module init exit work?
Okay, so these little magic things right here let the loader know where the entry points are for your driver. So they just need to match. And then these are things that your user can read out of when you do a mod info on your driver. So.
Okay, what do I do next?
Go up to init. Okay. So initialization is I want to say it's all the same. I mean, of course, there's a lot of hardware details that you have to worry about, but it boils down to a few basic operations. You have to request the operating system give you access to your device. And the way that we do that is, there's a couple of ways it can do it, and it's underneath, it's architecture specific, but because Linux as an operating system runs on so many different architectures, they've made it really portable for you. So in this case, what we're going to do, this particular device, this parallel port device, operates off of standard PC I/O ports. And so what we're going to do is we're going to tell the operating system that we would like to have exclusive access to a range of memory in the I/O port memory range. So for parallel port, this is 378 hex. And so what you're going to do is...
Do you want to show how you got that? No, we'll not worry about that. Okay.
Yeah. So what you're going to do is call the function to request memory. I believe it's request region.
Underscore?
Yes.
Okay.
And it should be the base address you're looking for, plus the length of memory you need, which I just asked for 8 here. And now I've forgotten exactly what the...
Okay.
thing, but
let's go to a driver that does that.
yeah,
Grep requests.
there's some final argument.
This is how you write drivers. You say, "What the? I don't know."
Yeah, I don't remember the API.
Oops. Well, I mean, yeah, you don't need to. Okay, phantom
Request
dots.
region.
Yeah.
Look, there's a comma, and it doesn't show up what the final argument is. But if you open up Sony laptop, looks like you'll be able to get what we need.
Sony laptop.
Yeah.
Request region.
Oh, there it is.
Okay.
Oh, a string, of course.
A string, hooray!
You have to identify yourself. In Linux, you can tell what drivers have claimed what memory region by catting a particular file on your in your proc file system, it's proc IO ports, and you'll see what the names of whatever these drivers are that have gotten your memory. So if you are having conflict, you know which one you need to decompile or get out of your kernel or whatever. So after we've requested the memory, then we need to map it so that we can actually talk to it. This maps that device memory into virtual memory for us, or IO memory. So if you're going to do that, because we're working on IO ports, this is a slightly different call than you would use with memory mapped IO. After we do the map, we can treat both the IO port memory and regular memory exactly the same because Linux has provided us with some portability APIs that let us do that. But for this, we're going to call a slightly different map routine, and this would be IO port map, IO port underscore map.
Okay, there we go.
And again with the base address, and again with the length, and I believe you need a string again.
Okay, hang on. Let's check.
Or maybe not. Yeah. You may not find this one actually in this directory because not many drivers are written using this older style anymore. Most of them are mem-mapped, but you might be able to look for. Let's see, what have we got here?
IO port map. Nope. No string. Okay.
Wait, there's one.
Yeah, start length.
Yeah,
That's it.
Okay. No string, so just the length.
Ta-da.
And of course, you want to reassign the result to your new to your IO base right here, which is a global, so we can always write to it.
Great. Okay, and that's
okay. Yeah. Now we're done with that part, and go down to the next step. The last thing that we need to do with this particular driver, that we'll do in this particular stage, is we need to ask for an interrupt line from the operating system. This one, because these are parallel ports, we're going to use IRQ7. If we were doing a more complicated implementation, we would be probing and stuff to figure out what interrupt line we were on, but we're not going to do that, and in fact, the reason I know this is going to be okay with IRQ7 is because I booted it with the regular parallel port driver and checked to see what interrupt it was claiming. And Val, if you'll do a quick demonstration on how you can do that by catting proc interrupts.
This is not the same machine, so my interrupt 7 is, or IRQ7 is not going to be. But
yeah, yours is different. See,
machine,
if I saw this on this, I'd be like, oh, I can't ask for interrupt 7, or I have to do shared interrupt.
Yeah.
But anyway,
but we don't.
That's how you can see what interrupts are, who's using what interrupt on your system. So in order to request an IRQ, it's request IRQ, surprisingly enough.
IRQ, it has a lot of arguments.
Oh my
I'm going
gosh.
to grep it pretty soon.
The cookies are done.
Well, don't worry, you have more, right?
We do. We have more. You can make multiple batches of
request IRQ while you take the cookies out. Okay, so request IRQ. I'm not even going to try. Whatever. I have something better to do.
We forgot plates.
There, actually, we did not.
We didn't. Oh, okay.
Ta-da.
Thank you.
You're welcome. Okay.
All right. So request an IRQ. You got that in there already, right?
Yeah.
All right. I think we're ready to move on.
No, I do not have. I don't know the arguments. There's like 5 of them. So request IRQ drivers.
Request IRQ. You should ask for the line, IRQ line that you're asking for, and I believe you need to give a string again.
Okay. So yeah, we've got the number, the interrupt handler function name, whether it's shared or not shared. We can do 0 for that, right? Driver name, a string, and then FM is an optional piece of data, a pointer to a piece of data that you can get in your interrupt handler. Okay, so IRQ, this is set up there. See, I've already forgotten. What's next? The name.
I'm not sure if it matters.
Oh, the function?
Yeah. I'm not sure if it matters that she remember at this point. So why don't you go ahead and push the next stage?
Oh, okay. We don't want to do request IRQ?
Well,
I should type this out. Platform.
Right. Go ahead.
Parport.
Do what you were doing.
Blinky interrupt? Oh, we're not doing in this section, are we? 0. I don't know, 0, probably string stuff. Null. Okay. Looks something like that. Quilt. So we're going to abuse quilt here. We're just going from one patch to another patch. We're not building them on top of each other.
This is like a cooking show where after they show you how to make something, they then walk over and say, and here my assistant has chopped up 800 pounds of potatoes and brought it to you, so you don't have to watch me chop 800 pounds of potatoes. That's okay.
That's fine. Emacs,
Yes.
-W, drivers, MISC, PowerPort, Blinky. There we go. Okay.
Okay, so now she's gone through, if you just go back to interrupts really quick, in it for a second, we'll
Sure.
just show them. It's all in there. This is everything that she did in the last one, only this time we were nice
error.
and we checked our return values and actually put in an error path, which you would always want to do in a good driver. But it's all exactly the same as what you saw demonstrated before. So at this point now, when you're writing a driver, it's time to actually talk to your hardware. So what we're going to do is we're going to work on a routine that will get triggered whenever we get an interrupt on our card. So
Go back up.
we haven't written this one yet, so we're going to write this one first. This is how to enable the card to actually generate an interrupt. So on the parallel port, if we want to enable interrupts on this card, we have to set bit 7 on its control port, which is 2 bytes up from the base. So what you're going to do is you're going to use IO write 8.
Okay.
We're going to do
Yes.
yeah,
Okay.
byte access. So IO write 8 to the I believe it's base and then value.
I think so too.
So
Like base plus 2?
base.
Or-
Oh, I'm sorry. It's value and then base plus 2.
Okay.
So it's 10.
Yes.
Base plus 2.
There we go.
That's all there is to it. Yay!
Woo, we have
All right.
interrupts.
Now let's write the one to clear interrupts. So after you've handled an interrupt, you need to make sure that you tell the CPU that you need to clear the line, otherwise it's just sitting there asserting you'll never get another interrupt. So if we want to clear the interrupt, what we're going to do is we're going to clear
All right.
bit 7 of the data port. So
IO
the
read,
first thing
right?
that I always do, usually when I do stuff like this, is I'll do a read, and then I'll clear the bit, and then I'll do a write. That way I only mess around with the one bit that I care about. So Val is going to show you how to do that.
Right?
IO read, yep. Base.
Or base. That's it? Right?
That's right. Yes.
Or 2? Or not? Okay, okay. And then we do...
Old and equal.
Yeah.
0x 7F.
7F. Okay, so that leaves all the bits set the way
That
they
leaves
were,
everyone
except for the one we
bit
wanted.
8. And we're going to write it back out.
8. How do we do that before?
Base, value, and then base.
Base.
No, just not
sorry.
base plus 2, just regular base.
Right,
All right.
right.
Okay, moving on. Now we're going to handle the actual IRQ.
Okay.
So I've left this stuff in there because they're just stubs to go to another place. But the way our IRQ handler is going to work is we're going to go off and do some blinky stuff. We're going to clear the interrupts, and then we're going to tell the OS that we're done. So we need to write, we wrote this one, we need to write this one. So if you go up and find blinky blinky,
There we go.
there you go. Okay. So on this particular device, if we want to make the lights turn on, we have to write a bit to the corresponding LED that's on there. So what I'm doing right here, just for simplicity, is I'm turning all the bits on. So FF will turn all 8 on. So 0 will turn them all off. Pretty simple, an on-off switch. So what she's got to do here is she's going to have to write LED state to base, IO base. I'm sorry,
Oh, right.
IO base.
Right.
Don't forget to use the one that we actually mapped.
Yeah.
The thing that it makes things a little bit more difficult, like it's not very difficult, but she's going to have to keep track of the state of the LED because next time we hit the interrupt, we want to be able to turn it off. So she's going to have to check now the value of LED state, see if it was on before. If it was on, she needs to turn it off. If it was off, she needs to turn it on.
Sure. Are we done?
That's it.
Great.
All right, moving on.
Okay.
Those are almost done too.
Oh, are we doing the next patch?
Yeah, next patch.
Okay, great. Oh, wait, hang on.
I'm sorry? Well, a character is an 8-bit. I mean, I would have used a U8, but she can get away with a character.
Characters are 8 bits. Okay,
Yeah.
deal. Oh, we're not going to do sysfs, are we?
I don't have the time on me, but we do have time to do sysfs if you want to.
Let's not.
All right.
I'm hungry.
All right, so wrapping up, you want to
Do you wanna show the final?
show them the final driver. Yeah, there's a lot of different ways you could do that, so that's your choice how you want to implement that.
Okay.
Okay, so this is the final driver that we have. This one we added a user interface to in order to allow your users to control the behavior of the LEDs. So we use this thing in Linux called sysfs. It's a virtual file system that exports a series of files, which are actually entry points into your driver. So you define these up front. And if we had more time, I would have shown you how to do it. But they're pretty simple. You follow, the formula for how to do it, and you'll have a store and a save routine. In this case, all we have is a write-only value. So we have this value called flashy that lets you, instead of just turning all the lights on and off, it will cycle through them and turn them on one bit at a time. So if the user sets flashy to something, then the value of flashy is changed, and then next time we handle an interrupt, flashy would detect whether or not the user wanted flash or just all on, and then it would do something. So let's take a look at Blinky now. So Blinky checks for flashy, and if flashy set, it cycles through cycles through bits 0 through 7, and it will write a 1, and then it will put a little delay in there so that we can actually visibly see the change. And then on the bottom one is the all on, all off. So we do that, and then we set the LED state based on what it used to be before.
Okay.
So everything else is basically exactly the same as I showed you before, only this time we put in real error handling.
Very important for your IRQ. We'd like
and
to
I'll
know.
just give you a quick demo on how the device works. Hold on a second.
I'll check your cookies.
Flashy now. Now we'll see what Flashy does. Sys. So you go to Sys, then you go to Devices, then you go to Platform, then you go to Farport Blinky, and you see the file Flashy, Echo 1, Flashy. All right, now. La la! Flashy! Woo! All right, so, obviously this isn't a really great real-world example, but my point is that writing device drivers really isn't that hard. A lot of people think it's magic, and it's really not. It's sort of following a formula, and in fact, I think that you don't have to be a very smart person to write a device driver. You just have to be careful. You have to be detail-oriented. You have to make sure that you follow the rules. You check for errors, because remember, when you're working in ring 0 or privilege mode, if you screw up bad. So I hope that you can see from this example that you could go out there and try writing your own driver, and it can be fun, and you can do it. So thanks a lot for putting up with our demo issues, and hopefully there's still enough of lunch left for you guys to enjoy it. Thanks very much. Oh. I should say, if you have questions, I'm happy to answer questions right now, too.
We can give a cookie to the questioners. Do you think?
If you ask a question, you get a cookie.
How long have you been writing drivers?
Kristen, I'll do the cookies.
Because you write them well. Thank you.
You give the cookies out.
I will, yes. It's because I'm your assistant.
That one.
Okay.
So I've been writing drivers since 1996. I worked I did my first internship at a network driver writing group within Intel, and it never occurred to me that I would go leave college and actually write drivers, but I did it, and I realized, because I was like everybody else. I thought writing device drivers would be way too hard, and it never even. I never thought that I would do it. I thought you had to be a hardware person to do it, and I'm just a computer science major. But I did it, and it was easy, and it was fun, and it was very gratifying. I get a lot of charge out of being able to actually write software that does something. you write a bit and something physical happens. Yay! I think it's very empowering. And so I started out right out of college. At that time, there was not a lot of market in the commercial area for Linux drivers, even though I was a Linux fanatic in college. And so from 97 or so to 99, I worked on NetWare, which was a good experience because NetWare is a very primitive operating system, and I learned how to do everything in assembly, and it was great. But I was very appreciative of moving to Linux where we had actual C. So that's the answer to your question. Anyone else? Cookie.
Oh, hi. I feel like I'm on the spot. Do what? Oh, okay. By the way, excellent presentation, and don't worry about anything that happened in there. I already forgot it. This is really amazing.
Smart people don't do demos at conferences.
It was excellent, at least for me. My question, I got two of them real quick. First off, I'm just curious what... Well, I'm not doing it. No, I'm just kidding. What is the most complex driver that you've written per se? And then I'm curious, in the Linux space, open source space, what is the most complex driver you're aware of, and why? Just curious.
So the hardest driver I've ever written was a DSL driver. It had several parts. It was in many cases it was complicated, even though it didn't need to be, because of the desire of the desire to be flexible makes things hard on you. So in this particular case, we weren't sure what PHY manufacturer we were going to use on the final chip. So we had to design the driver in order to have a DSL's driver is two parts. There's the ATM part. It actually looks like an ATM device. And then there's the physical part, which is sometimes a DSP. At any rate, you could divide the driver up into two parts. So you could have a driver that controlled the PHY, and you could have a driver that controlled the upper part. And we weren't sure what PHY chip we were going to use. So I had to write like 3 different PHY drivers, and they all had to work with the same upper part. And then on top of that, with DSL, you can have many different protocols on top of DSL. You can have PPPoA, PPPoE. You could have, all these other things. And also on top of that, you had management protocol that you had to worry about. You had the ATM, OEM management or whatever. And so there was all these different parts to this driver that made writing this driver very complicated. And that's the hardest one I've ever done. But that was a long time ago. Drivers in general, I don't think, are that hard. And when they become hard, you have to ask yourself why. Because to me, it seems like at that point, little flags should be going off saying, maybe I'm over-architecting this. And as far as what is the most complicated driver I've seen inside the kernel, I haven't seen too many hard ones, but I have to admit to having never looked at the video. And I have this gut feeling that the video stuff is the hardest. So generally, if drivers seem to be hard, like I said, it's because they have over-architected them. They have added too much junk into the driver. My personal philosophy is that drivers should be as stupid as possible and do as little as possible. You should put anything that requires much thought, and especially if it's not performance sensitive, into user space.
Hi.
Hi.
This might be a little out of scope, but if I had a bit of hardware and there was no driver for it under Linux, what would be a good way to start thinking about writing a driver for it?
Oh, so you have a piece of hardware with no driver, and you have the desire to write a driver for it, or you simply have a desire to get a driver for your device?
Well, preferably to have someone else write it, but
okay,
to write one.
Because I have a good answer for you for that. Right now, I don't know if many of you are aware of this, but last year Greg Crowe-Hartman launched a project called the Linux Drivers Project, and the idea is that he will write for free. He and a team of about 300 happy developers will write for free any driver that you want for any piece of hardware that you're willing to give them the specs for. And they'll even sign NDAs through the Linux Foundation. So if you have a piece of hardware and you guys have no device driver expertise and you want a Linux device driver, go to the Linux Driver Project. Those people are dying to start working. He's got a lot of students, a lot of people who want to learn to write drivers, and Greg himself is supervising everything, and he's a very experienced person. So you're going to come up with a good quality product at a very good price. So if you would like to write it yourself, then I suggest that you start by purchasing Greg Kroll-Hartman's book, Linux Device Drivers, and you just, like I said, rip off a driver that looks exactly like it and start going. It's not that hard. Yes?
So you've been programming whatever that piece of breadboard is that's hanging off there. Is that, like if we wanted to get into writing device drivers and wanted to turn on flashy lights, is there somewhere we can go to find circuit diagrams for something we can put together ourselves?
Yes, actually, this particular device is modified from the description that you can find in the Linux device driver. Linux device driver shows you the schematic of the parallel port. It tells you how to hook up some LEDs to it. The only thing that I did slightly different is in the hardware point is add this little switch. They had you actually just take two wires and go kink. I got fancier. And then, of course, I changed the behavior of the driver that they were writing in Linux device drivers. But if you want to make something similar to this, actually at this point the hardest part is finding a machine that still has a parallel port on it.
I know I shouldn't ask another one, but I can't help it. I'm extremely interested in writing very interesting programs on like a mobile phone and doing device drivers where the phone interfaces with hardware that's external to itself. But I have not been able to find a phone that allows for that. I'm curious if you've encountered anything like that and what phone it is and any ideas on how to begin to do that?
I haven't really looked at the phones. I know that there are some phones that will run Linux. I believe one of the Nokias, the 800 or something, will do it. I don't know as far as external. It looks like somebody here might have the answer to that. Or does anybody know the answer to that? Who has the mic?
We're actually here with TI had a space with some of their OMAP stuff, and they power some of the Nokia internet tablets and the phones, and they're actually sponsoring as kind of a skunkworks project, this Beagle board that supports a lot of what you're doing. So building up these drivers around the peripherals around their new OMAP 3, and so there's a lot of activity there, and that's a great community place to participate.
Thanks. Yeah, and I would say if you don't want that particular one, look for a phone. And I don't even know if they make these, but maybe it has a FireWire or some kind of mini USB on it, which then you could do USB. I don't know if any of them make that, but I would do that if I was making a phone. One more question.
So Linus famously said that debuggers are for wimps, and that he debugs the kernel by squinting very hard and sort of encants the solution. I believe that's the case, but for the rest of us, what support is there to debug your drivers?
So the good news is that Linus has changed his tune, and he's now going to be allowing an actual kernel debugger to be put into the source tree. I personally, I told you when I started out working on NetWare actually builds a debugger into their operating system, and so I got kind of used to having a debugger available. But after I moved to Linux all those years ago, I've just gotten used to not using one. You can connect up debuggers. There are those out there that are external to the source tree that you can set up, like KGDB, or there used to be another one that SGI put out. I don't know if they're keeping up with the patches. But it will soon be very easy for you to use a debugger because Linux is going to now include a debugger in the source tree. So those of you who like debuggers, don't despair. But, to be fair, not having a debugger does force you to inspect your code more. And I think that it would be sad if we stopped doing that just because we had debuggers. So I think it's really important to do both of those things. Okay, well, I guess we're out of cookies. So thanks a lot.